Hi, Physics 2, Mr. Janowski here. This is part 4 of the Chapter 37 slides. So in the last part, we learned how a generator works and how it is kind of the opposite of an electric motor. And in this part, we're going to learn about another very important type of electric device. So let's get started with that. So if you have an electric motor, what is the input and what is the output? An electric motor is going to input electrical energy and it's going to output mechanical energy. So we're going to supply electricity to this thing and it's going to make something turn. And once you have something turning, you can get all clever and get it to do all kinds of other things too. But that's what an electric motor is. So what are the input and output of an electric generator? Well, it's basically the opposite. An electric generator is going to input mechanical energy and it's going to output electrical energy. So learn to see these things as, very complementary in what they do and what they're for. So who liked DC? So this old stodgy looking gentleman up here in the top right, this guy liked DC, and his name is, of course, Thomas Edison, and everyone hates him now. And at the bottom right, this very debonair, suave looking fellow, he liked AC. And what was his name? This is, of course, internet celebrity Nikola Tesla. And during his own life, before the internet, he did very many important things as well. So yeah, Edison liked DC, direct current. Tesla liked AC, alternating current. So here in the US, what is the RMS voltage? RMS meaning root mean squared, basically the average voltage that we get out of our outlets. We get 120 volts. And what is the frequency of our voltage here in the US? It is 60 hertz, so 60 cycles a second. So that's how we do it here in the US. And I think in Canada and Mexico too. I've never actually been to Canada or Mexico, but I think everyone here in North America is doing the same thing. In other parts of the world, frankly, in most parts of the world, they're going to do something different. They're going to do maybe 220 or 240 volts at 50 hertz, 50 cycles a second. But here in the US, 60 hertz, 120 volts. So if you have this AC voltage coming out of the wall and you need to turn it into a DC voltage, what kind of device you're going to use? You're going to use what's called a rectifier. So this would be called a half-wave rectifier because your input is this up and down sine wave thing, and this is only keeping the ups. So it's not a flat constant voltage. There are ways to make that happen. But yeah, this is just one type of rectifier. We're going from voltage that goes both ways to voltage that only goes one way. So we also talked about generating power and power transmission. So now we know what this thing's about. We know what a generator is. It's going to turn mechanical energy into electrical energy. And then we need to send it to people. So we're going to go from this stage to this question mark here. And then we're going to transmit it. And then there's going to be another question mark kind of thing over here. And then finally, the end users, the businesses and the households that use it are going to do it that way. So this red question mark here represents this device that's going to take the voltage coming out of here and step it up to a much higher voltage. And then it's going to be transmitted. And then this device here with the green question mark is going to take that high voltage and step it down to a lower, more manageable voltage, more appropriate for the end users. So what do we call these devices that either raise the voltage or lower the voltage? These things are called transformers. So yeah, the topic for today is transformers. So what is a transformer? A transformer is a device for increasing or decreasing AC voltage. Has to be AC voltage. So it's going to consist of two coils of wire called the primary and secondary coils, and they're going to share an iron core. So think of the primary. So in this picture, it's the red one on the left. So this primary is basically your input. And over here on the right, the secondary is your output. So primary coil, secondary coil. And notice that we have different numbers of turns in each of these coils. So in this case, the primary has many more turns than the secondary. So more turns on your input side than you have on your output side. So these won't ever have the same number of coils or the same number of turns. That would defeat the purpose, as we're going to see. But in this particular case, the primary has more turns than the secondary. There are other cases where you would do it the other way, and the primary would have fewer turns, and the secondary would have more turns. But yeah, that's what a transformer is. It's a device for increasing or decreasing AC voltage. So we've got AC currents. So over here to the left, we have something generating power, and it's coming in here. So we have AC voltage coming in here. The fact that the voltage keeps changing and the current through this wire keeps changing means the magnetic field being generated by this wire is going to keep changing. So ultimately, the relationship between the amount of flux you have and the rate at which the flux is changing with respect to time over here on the left side is going to be given by this formula. So in this formula, change in flux over time is going to be related to the input voltage and the number of turns by this relationship right here. So yeah, current's coming in here, and the current's changing because it's AC, and that's going to cause a changing flux. Now, this same amount of flux is going to be picked up over here, and that's going to induce an AC voltage with the same frequency being in italics there, in the secondary coil. So yeah, different number of turns, different voltage as it turns out over here. But what's going to be the same through here is the rate at which the flux is changing. Delta phi sub B over delta T. So yeah, this is, an electromagnet. Well, this coil going around here makes this an electromagnet, and the magnetic field that's being generated over here is being picked up over here. So yeah, this ultimately is really why Tesla won. This wouldn't work with DC voltage, because if we just had a DC current coming in here, you would have a constant magnetic field, so you wouldn't have a changing flux, a flux that was changing with time. So this is, Tesla's big advantage. So yeah, up with Tesla, down with Edison. So the voltage induced in the second coil is going to depend on how many turns it has. So on the left side, we created this changing magnetic flux with time. On the right side, we're going to pick up that magnetic flux with time, that changing magnetic flux with time. And so we have this expression that relates the voltage in the secondary coil and how it relates to the number of turns in the secondary coil and the changing flux. So if we divide our expression for voltage on the secondary side by voltage on the primary side, we get this, and then delta phi, delta T cancels, and you end up with V sub S over V sub P is equal to N sub S over N sub P. So yeah, this is the transformer equation. This is one of the transformer equations. We'll get to another one. So this relates the input voltage of the primary coil to the output voltage of the secondary coil and the number of turns you have in each coil. So yeah, this is neat. We can take an AC voltage and change it to a different voltage just by varying the number of turns we have on either side of this transformer. So if we're looking at this, so look at your expression, this transformer equation we have here. Is this transformer going to increase or decrease the voltage? So 3, 2, 1, it's going to decrease it, because in this case, we have fewer turns on the secondary side than we do on the primary side. So this over here, N sub S over N sub P, is going to be less than 1, which means the voltage we get coming out of the secondary coil is going to be less than the voltage that went in on the primary coil. So this is going to decrease the voltage. So this would be a step-down transformer. If you wanted to make a step-up transformer, first, the thing that's pictured here is a lot like this one here. So this is the one that takes the high voltage from the transmission lines and lowers it to a voltage that businesses and houses can use. So that's the step-down transformer. If you wanted to make this other one, the one that took the voltage coming out of the power station and you wanted to really step it up in order to make it easier to transmit, you would do it the other way, which means you would have many more turns in the secondary coil than you had on the primary coil. So if we can increase the voltage or decrease the voltage, but specifically, if we can just increase the voltage just by changing the number of turns, are we getting something for free? It kind of seems like we're cheating here. Are we cheating? And the answer, of course, is nope, we're not cheating. There's no universal law, there's no one with everything law that says voltage must be conserved. So, yeah, you're allowed to change voltages. That's not breaking any laws. Energy, on the other hand, must be conserved. So energy is the thing that has to be conserved. And in this particular application, we're not going to so much be interested in the energy that's being conserved. I mean, in a sense, we are, but we're more directly interested in the rate at which energy is being used. So, what is the name for the rate with respect to time at which energy is being used? We call this power. So, yeah, the power has to be conserved. So the amount of power that's going in over here has to be the amount of power that's coming out over here, not the voltage. The voltage can vary, that's fine, but the energy and the power have to be conserved. So how does power relate to current and voltage? This is one you should remember. This is Watt's law. There's Watt. This is PIV. P equals IV. So keep that in mind. We have this relationship. This is our transformer equation right here relating the input. I'm sorry. Well, I have the output over the input over here. So the output voltage, the secondary voltage, over the input voltage, the primary voltage. And we have this relationship for P. And I've just told you, well, energy has to be conserved, so power has to be conserved. So we can replace these V's with P over I's because PIV. So if P equals IV, then V equals P over I. Do a little bit of algebra. We end up with an ugly fraction over a fraction. You do the stuff, you keep switch flip or whatever, and you end up with this other expression over here. So this is the other transformer equation, only this time we're not talking about how the secondary and primary voltages relate. We're talking about how the secondary and primary currents relate. So sometimes this is the more useful form of this equation. So in both of these cases, I've written the secondary thing over the primary thing on the left side. Because if you're making one of these, you're going to know what your input voltage is, and you want to get to an output voltage. So that's why I did the output, the secondary one, over the primary one. So you have V sub S over V sub P and I sub S over I sub P. Now notice if we're looking at the right-hand side of both of these equations, the ends are flipped. So in the first transformer equation, you had N sub S over N sub P, and in the second one, you have N sub P over N sub S. So be very careful when you're doing these. That you're thinking of which quantity you want. Are you dealing with the voltages or you're dealing with the currents? And you grab the right formula and you write your subscripts very carefully. Because, this is a super easy one to mess up. So, again, back to the do now questions. Here in the US, we use 120 volts RMS at 60 hertz. So it's AC voltage. Now, the appliances we use, whatever it is, it's probably going to want a much lower voltage. Some things do want higher. TVs often want higher voltages. Your microwave will want a higher voltage. But most of your small appliances are going to want a lower voltage. And they will often want DC instead of AC, which means this power adapter thing here, it's going to be doing a second thing. We already talked about, what the rectifier does and how that turns AC into DC. So here's a simple one. Here's a more complicated one that does a better job. That's what the rectifier does. It turns AC into DC. But you're also probably going to need a transformer. So here is a schematic symbol for a transformer. Input coil over here, so primary coil over here, and secondary coil over here. Same deal over here. So there's a lot going on in this simple little device. There's probably a transformer stepping the voltage down in most cases. And there's also a rectifier that's turning the AC into DC. So, can you remember, what are your transformer equations? There's one that relates the voltage, and there's one that relates the current. And which one is N sub P over N sub S, and which one is N sub S over N sub P? Well, here they are. If it's voltage, it's V sub S over V sub P is equal to N sub S over N sub P. And if it's current, it's I sub S over I sub P is equal to N sub P over N sub S. So, they're flipped. Just be careful when you're grabbing these equations and doing the problems. And the second question, transformers don't conserve voltage, but they do have to conserve something else. So what is the other thing they conserve? Energy, and therefore power. So, yeah, this very one with everything law that we learned last year, the conservation of energy, still true. There is no conservation of voltage. Voltage is not something that, that can go up or down. You don't need to conserve voltage. But energy and the rate at which energy is used, power, needs to be conserved. So now you know how more of your electrical devices work, and hopefully you found this interesting.